The question that I have is, what does a consolidation test reveal? Let's talk about the fundamentals of the compressibility of clays and the process called consolidation. We're going to do a series of consolidation tests in the lab, all right? This is what we're going to do. We're going to take a certain amount of dry clay particles like kaolinite, mix it up with a lot of water to create what we call slurry. What is a slurry? Slurry is basically a semi-liquid mixture of clay particles and water. So basically it has a consistency between a clay suspension and a paste. So you want to mix it up in a professional mixer so that in the end we have a homogeneous slurry. We're going to pour this up into a consolidation cylinder that looks like this and apply a loading in order to consolidate the slurry. Well, what do I have in the cylinder? Well, I have the cylindrical part, usually made out of plexiglass, but it could be made out of aluminum if you want to. All right. And this cylindrical setup has a base that has a drainage line. The drainage line would allow water to drain through and come out of the cylinder. And at the top and bottom, we have an arrangement consisting of a porous plate, porous stone, and a filter paper. Filter paper so that the soil doesn't clog up the porous stone. Porous stone so that the water can freely drain either vertically up or vertically down. The porous plate over here is attached to a rod that could be used to apply a vertical load. And the clay slurry is right here. We're going to increase the vertical stress sigma V a little bit and plot the variation of vertical settlement with time. Supposing, say, at the very beginning, the clay slurry has a void ratio of E naught. In other words, at this point, the void ratio is E naught. Say we increase the vertical stress from 0 to 2 psi. And this is what happens. Vertical settlement increases and then it tapers off at some point. For this to happen, it might take a couple of hours, maybe 24 hours, or maybe even a couple of days. By the time we are done with the theory here, you will have a pretty good understanding of the variables controlling the time here. As the loading plate settles, the soil becomes denser and the void ratio decreases, gradually decreases. And this process is what is called consolidation. Say eventually the void ratio decreased to a value of E1, which is E naught minus a change. How do we calculate this delta E? Well, we use the principle of proportionality. Here we have the soil sample, and this sample has a length of L. I'm talking about this sample right there. And from the vertical settlement, I know the change in length, right? Delta L. Okay? Here we have the phase diagram. And this part is the solid part, which we are going to take as 1. And then this part is the void part, right? So volume fraction wise, that's going to be little e. Say when this happens, void ratio changes delta E. Here is the application of the proportionality principle. Delta E over 1 plus E must be equal to delta L over L. So this allows you to calculate the change in void ratio from the vertical settlement readings. Now let's come back to the settlement curve again. Once the settlement tapers off, we're going to increase the pressure again from, let's just say, 2 psi to 4 psi. Similar sequence of events happen. The settlement increases and tapers off, and then the void ratio decreases from E1 to E2. Say we carried out the consolidation for 2 more load steps. Typically we would double the load, like we will go from 2 to 4, 4 to 8, 8 to 16. I'll explain the reason in a little bit. Since I have used numbers for the vertical stress, let me also use numbers for the void ratio. These are just approximate qualitative numbers. So we have some values of void ratio corresponding to the values of vertical stress, and we can plot the two in order to establish a relationship, right? When you plot E against sigma V, you're going to get a curve that looks like this. It turns out that if you plot the data on a semi-logarithmic space like this one right here, the curve turns into a straight line. So we basically have an exponential relationship, right? And this is the reason we keep doubling the load also. So when you double it, the change in void ratio between load increments would be approximately the same. At least it will be in the same order of magnitude. This relationship is what is called the compression or Virgin compression line. Since we have a straight line between E and log sigma V, we can write down a simple mathematical equation relating the two. In other words, there is a linear relationship between E and log sigma V with the slope of C sub C, the slope is negative, right? And with an intercept E star, the geometrical meaning of E star is it is the void ratio at sigma V equals 1. The constant C sub C is what is called the compression index. The higher the value, the higher the compressibility of the soil. In other words, for a given increase in the vertical stress, the change in the corresponding void ratio is going to be higher if the value of C sub C is higher. So what kind of values are we talking about? Well, it could be as low as 0.1 for low compressible clay to as high as 10 for highly compressible clay. Here are some examples. The next question is, what happens if I unload and reload? These things happen in real world, right? Say instead of going all the way to this point, I'm going to unload it from this point. In other words, I'm going to start from slurry, load it up to 8 psi, and then unload it. Say I unloaded from 8 to 4 and then 4 to 2. This is the kind of curve that you get. An important observation here is that it does not go back along the original curve. Now this is because soil is a plastic material, and therefore when we load it and unload it, the void ratio does not go back to the original value. There is a permanent change in the void ratio. This is what happens to plastic materials, right? It turns out that this curve too turns out to be a straight line in the semi-log space, and therefore we can write this in the form of a linear equation as well. The slope here is called the swelling index because this is really swelling, right? Here's the meaning of E double star. In other words, if I extend this line, the intersection of that line with sigma V equals 1 vertical line is D double star. The soil is now described as an over-consolidated soil. Well, what do we mean by that? Well, this soil specimen has been already loaded to a vertical pressure of 8 psi, even though the vertical pressure that currently exists on the specimen is only 2 psi. To quantify the degree of over-consolidation, we define a ratio called over-consolidation ratio, abbreviated as OCR. OCR is defined as the ratio between this pressure sigma p, which is the maximum vertical pressure to which this specimen has been consolidated or compressed in the past, to the current vertical pressure. Sigma p is referred to as the pre-consolidation pressure. So for an over-consolidated soil, OCR would be greater than 1 because sigma p would be greater than the current pressure, right? When they are equal to each other, the soil is described as a normally consolidated soil. In other words, if the current pressure happens to be the maximum pressure to which the specimen has been compressed in the past, it is called the normally consolidated soil. Next question is, what happens if I were to reload from this point right here? You get a curve that looks something like this. 2 points to note here. One, even though this curve and this curve, in other words, the swelling curve and the reloading curve, are not exactly the same, for analysis purposes, they can be assumed to be the same. All right, so that's point number one. The second point is that on the swelling curve, right, swelling curve seems to meet this virgin compression curve at a distinct point. So just by looking at the swelling curve and the virgin compression curve, you can tell for sure where sigma p is. On the other hand, there is a gradual change on the reloading curve, and therefore it's kind of difficult to identify exactly where sigma p is on that curve. That is my second point right here. So the second observation calls for a special procedure for identifying the point where sigma p is, and in fact there is one, and I'll talk about that a little later. Also, I want to point out that the pattern of behavior is the same regardless of where you unload it from. For example, if I unload it from here, the unloading curve, the swelling curve looks like that, and then the reloading curve looks like that. If I unload it from here, the swelling curve looks like this, and the reloading curve looks like this. And if I were to take these green curves and plot them in the semi-log space, they all turned out to be straight line, but not only they are straight line, they are approximately parallel to each other, and therefore they could be assumed to have the same slope. In other words, the swelling index is approximately the same regardless of where you unload it from.